In the name of Allah, in this video, we are going to discuss the fundamental data types. That is the chapter 12 of software construction and development. The topics that will be covered in this lecture are numbers in general, in which there are subtopics like anticipate divide by zero errors, make type conversions obvious, avoid mixed type comparisons, heed your compiler's warnings, and the next topic is integers, in which we are going to check for integer division. We are going to check for integer overflow and check for in overflow in intermediate results, and then we are going to learn the methods by which we can create our own types. So first of all, we should know that what is fundamental data types. Fundamental data types are the basic building blocks for all other data types. We know that the different types of data types like integer, string, boolean, and the character. These are the fundamental data types that are going to store according values in them, and all the other complex data types are derived from these fundamental data types, and they are very important to be learned effectively and completely. And we are going to discuss the tips to use numbers which are less error prone, and we are going to learn that how we can create our own types. So first of all, what's numbers in generals? We have to avoid magic numbers. Magic numbers, we know that they are literals. uh, we are told to avoid these magic numbers in our code or literals in our code because of some reasons. Instead, we have to use named constants. These literals, because it avoids creates much confusion in our code. Therefore, we have to use named constants. There are many advantages to use named constants instead of literals. The first one is it's easy to change, and our code will be more readable. For suppose we are having an example here for I equals to 0 to 99, we have to do a code like this. We can guess that 99 refers to the maximum number of entries, but the expression for I equals to 0 to maximum entries minus 1, we have to do some code here. It leaves no doubt. Even if you are certain that a number will never change, you get a readability benefit if you use a named constant. So as compared to this code which has used literal 99, uh, here we have used named constant. It is much readable and easy to understand than this one. Therefore, we have to prefer named constants instead of literals. And also changing, if you want to change the values of maximum entries, or we have to change the values of this 99. This maximum entries is much easier to change because it can happen that we have used in our code in many places this maximum entries. So instead of literals, like we have to use this one, because literals in each place you have to go and change those values manually. But in maximum entries, wherever we have defined our named constant, like const maximum entries equals to something, if we wherever we have defined our maximum entries, if we change the values there, so automatically wherever we have used this named constant in our code, those values will also be changed. So it's much easier to maintain, and it's also readable. Therefore, we prefer named constants instead of literals. Another tip is we have to use hard-coded zeros and ones if we need to. The values 0 and 1 are used to increment, decrement, and start loops at the first element of an array. The 0 in for I equals to 0 to constant do is okay, and then the 1 in total equals to total plus 1 is okay. A good rule of thumb is that the only literals that should occur in the body of a program are 0 and 1. Any other literals should be replaced with something more descriptive. So here we are told that the only literals that we are going to use in our program are zeros and ones. Zeros are for the initialization of our loops, and the ones are for increment and decrement of any value. Except these literals, we are not allowed to use, or it's not guided that we have to use other literals instead of this one. We are told to use named constants which are much descriptive than than the literals. Another tip is we have to anticipate divide by zero errors. We have to think that the integer that we are going to divide any number with, that is zero or not, because we know that any number divided by zero gives infinity. And if we are going to face such situations, in that cases we have to write exception codes to handle our code. Therefore we have to uh, keep in mind about these errors, and we have to write code for that. We have to make tab conversions obvious. For suppose we are going to change an integer value to a float value, so the type conversions or typecasting must be more explicit, which should be readable to other programmers. Like this example, which is in C++, x plus float of I equals to y is equals to x plus float of I, and y is equals to x plus cs of NGI, which is the code of Visual Basic, and it's much more explicit type conversions, which is more obvious. Another tip is we have to avoid mixed type conversion comparisons. If we are comparing two values which are of different data types, we cannot compare them. The data types must be same in order to compare their values. Like suppose we cannot compare the integer with the string. We cannot compare float with the integer. So first of all, we have to manually convert integers into float, and we have to convert float into integer if we are going to store it in or compare it with the integer value. So we have to make them comparable with one type of data type, and then we have to compare them. Otherwise our compiler will give errors, so we have to keep in mind about these errors. Another tip is we have to heed our compiler's warning. Many modern compilers tell you when you have different numeric types in the same expression, pay attention. Every programmer has been asked at one time or another to help someone track down a pesky error, only to find the compiler had warned about the error all along. Top programmers fix their code to eliminate all compiler warnings. It's easier to let the compiler do the work than to do it yourself. So whatever warnings the compiler are giving us, the modern compiler, they mostly gives us warnings that here you are going to you're supposed to do this error. So therefore compiler gives warnings, so we have to take notice of those warnings, and we have to avoid those we have to try to write code that should not create such warnings, because in um, further programming, those warnings can be a cause for creating errors. Therefore, we have to avoid such warnings, that such warnings should not occur at all. Okay, next comes our integer. How we have to use integer. We have to check for the integer division. When you are using integers, like suppose 7 by 10, this does not equals to 0.7. Although in arithmetic world, the 7 by 10 equals to 0, but in programming world, 7 by 10 does not equals to 0. Here I have made a program on these a equals to 7, b equals to 10. Although if we divide 7 by 10 in a calculator or in arithmetic world, it gives 0.7, but here we are getting 0, which is unexpected. So we have to keep in mind about such errors that can create a big issue in our code or in our calculations, especially in banking and e-commerce side. Such errors should be avoided. So for these um, solution of this problem, but what we are going to do, that we have to divide the division. We have to use the division at the end of arithmetics. Other arithmetics should be done before division, and then we can get the uh, exact or true or correct value. And then we have to check for integer overflow. The problem comes up when we multiply two numbers that produce a number bigger than the maximum integer. For example, if we multiply 250 with the 300, the right answer is 75,000. But if the maximum integer is 65,535, the answer you will get is probably this one because of integer overflow. 75,000 minus 65,536 equals to this one. So sometimes this happens that we are going to store values that is higher than the range of that integer. For suppose we are going to store this value 75,000 inside a number that is not having this much range, so it will be overflow. Therefore, while using integers, we have to keep in mind that whether this integer is going to hold the value that I am going to store in it or not. If it is not going to store such large values, such a large range of values, we have to use another integer for that to avoid such errors. So here are integer types and their ranges. The first one is signed 8-bit integer, which is having the range of minus 128 to 127. Signed integers are the integers that are having both the negative and positive values, but unsigned integers are the ones that are only having positive values. Similarly, we are having 8-bit integers, 16-bit integers, 32-bit, 64-bit, etc. They are going to have different ranges. So we have to keep in mind about their ranges and give them values according to their ranges. Another tip is a check for overflow in intermediate results. Sometimes this happens that there can come overflow in between our calculation. So we have to keep those errors in mind and use values or store values according to the range that an integer is having. For suppose here we are having a Java program in which term A and term B, they are having values, and again the result of the multiplied form of these two numbers are stored in this product, uh, and we are going to have the product as a result. So here it doesn't give exact and correct value because the multiplication of these two numbers is going to be stored in a number product that is not having the range, which is its result. Means the product is having less range than the result of these multiplication numbers, then the multiplication of these numbers. When we divide this by this one, then we will get this one minus 727, which is the wrong answer. So for this we have to use a much larger range of integer holding range, uh, where we can store this value, because the answer of this one is this one. So we have to use a value, an integer which is of this range, and then we can get the correct answer. So the purpose of this slide is this, that sometimes this can happen that the error or overflow of integer can occur in between our calculation. So we have to keep in mind and use data type of uh, much higher range, which is comparable with the result of this calculation. The next topic of this slide is creating your own types. How we can create our own type. In C++, we were having the type def keyword, in which we were defining our data types and then our own type, and then we were going to store values inside the coordinate. This type definition declares a new type coordinate that's functionally the same as the type float. To use the new type, you declare variables with it just as you would with a predefined type such as float. Here's an example. Okay, here is example. We are having a method routine one in which we are having three different values: latitude, longitude, elevation, which are having the data type of coordinate. So likewise, we can create our own type. Now this coordinate is having the type of float which were defined by our own selves. Another routine in which we are going to create x coordinate, y coordinate, z coordinate. These all are having the float values. In this code, the variables latitude, longitude, elevation, x, y, and z are all declared to be of type coordinate. So here are some guidelines for creating our own tabs. The first one is create tabs with functionally oriented names. Means whatever functions the tabs perform, tab must be as per that function, like a float for currency, integer for age, and others. Um, Whatever function a tab is going to perform, we have to give such data type to that named to that type. For example, in currency, we are going to have point values. Therefore, we have to define float for such types. And integer and age is going to be a number. So we have to define integer for age, and similar other functions should be defined. Other types should be defined, which must be comparable with their values. Another guideline is we have to avoid predefined types. A declaration like coordinate x tells you a lot more about x than a declaration like float x. So we avoid predefined types as much as we can and use our own types. Because this coordinate x, this is much more clear that x is going to be a coordinate which will be having float value. It is much readable and much explicit that it's coordinate x than the float x. It's not that much clear. Therefore, we are going to use we are going to avoid the predefined types, which is float. Sorry, which is float. And the next guideline is don't redefine a predefined type. For suppose we are in a code where we are having integer x. Again, we are not supposed to define our own type as integer x, because it will be repeated and there will be error. There can be confusion. Another guideline is we have to consider creating a class rather than using a type def. Simple type defs can go a long way toward hiding information about a variable's underlying type. In some cases, however, you might want the additional flexibility and control you will achieve by creating a class. So in this last guideline, we are told to use a class for creating a type, and then we have to use that tab in our further programming. Thanks for watching.